Let's take a look at lesson 5.2, the definite integral. So from 5.1, we introduced this notation of an infinite sum, where we're adding up an infinite amount of rectangles or pieces together to approximate or estimate the area underneath the curve. And so what we move now into is a formal kind of notation, this notation here, the integral notation, to represent the infinite limit here. So the key thing now is when you see this, what we call this definite integral, this form, right? The integral of the function from A to B, you have a picture in your head as that we're trying to calculate the area underneath the curve. So it's always important to maintain that visual and that we're using an infinite amount of pieces to estimate that area underneath the curve. But we learned in calculus, these limits, the idea of using limits, we can then use that to get a precise answer, right, for an infinite amount of rectangles. And so we have this definition of the definite integral. The function is integrable, right? It's an integrable function, right, if this limit exists. And so that's what we'll be using now and becomes an important piece this last unit of our course, right? Being able to understand, one, the notation, that it represents the area underneath the curve, and then we start to then learn what does the area represent, right? Why would we care about finding the area underneath the curve? Leads to this theorem: if f of x is continuous, then a function is integrable. And then we can find its integral, right? This definite integral. And so evaluating them is what we've done. You're doing on the concept mini exam, finding the area underneath the curve. Now we're still using, again, a right-in approximation. We still haven't found it. On the next lesson, we find out actually how to calculate it exactly. And so all you see here is just, again, that using that notation. And again, looking at this, it's still using infinite sums because this is just telling you find the infinite sum of f of x squared from 0 to 2, right? Using a right-in approximation, which we learned to do in the previous unit. And then there are formulas here, so don't worry about memorizing these infinite sum or these sum formulas, which we saw in 5.1. It allows us to come up with some exact representation of the function, which then allows us to calculate the limit. So we first had to convert that sum into some function that we can find the limit of. So we're going to move away from that, just understand the idea of calculating the area underneath the curve. We're not going to focus on these sums and memorizing those formulas. But again, it's a really great exercise to go through. And then being able to do that following that kind of notation. We're really going to be interested in more this example, like where we have a function and then knowing what its graphical representation looks like. Then we can actually calculate, right? Because we have a formula for a circle. This turns out to be a semicircle from 3 to 6. So find the area underneath the curve, and then you use your formulas to do that. And then when there's lines, then you end up using trapezoids or triangle formulas to actually calculate the area underneath the curve. And so that leads us back to, again, this area, which we still haven't done fully about explaining its power, but we don't do that until after we kind of know the exercise of actually calculating them. And so sometimes the area under the curve is actually area above the curve. So when it's below the x-axis, we're looking at areas above the curve. So I want to make sure you get a sense of that, right? Below the x-axis, we're looking, it's really above the curve or below the x-axis, above the x-axis, below the curve. So I want to make sure you don't get too confused with that notation. When we actually calculate that, anything below the x-axis is considered a negative value. So you can see here, you'd have area 1 and area 2. The total area underneath the curve, right, in that term from 0 to 2 would be A1 minus A2, or plus negative A2, or plus negative A2 is a negative area. So we have, again, what we call this net signed area. You would add those up two together. And so that's going to emerge when we have these lines like this that go above and below the x-axis. Here you have triangles to represent those areas. So keep that in mind about the area underneath the curves. Okay. So one thing we end up using an application of a definite integral is about finding displacement, how far an object travels. And we'll see that in the next section, that we will find the area for some reason represents the total distance, how far an object travels if we know its velocity. So we end up using the integral of a velocity equation to find its displacement, how far it actually travels. And that will be kind of an application we use. And that's what it's kind of talking about here. We have different velocities. How far does it actually travel? And that total area would be its distance. So you'll see when we're finding a total area, we end up caring about the absolute value of that function. I just want the positive aspects of it. And so you saw that again too on our concept exam. This absolute value allows us to find the area above the curve if it's below it. So it turns out to be a total area equation, which we end up using. You can do it many ways, calculate the positive, negative, and know that I'm finding a total, and then just convert that negative to positive, or put the absolute value around that f of x, which then means the graph actually would look a little different, right? So you can see when we do that, you will see you end up with a slightly different representation. But again, it's the idea of understanding what we are trying to solve. Now that we have this new notation, any new notation in mathematics leads us to rules and different ways, just like derivative rules, right? We're going to have integral rules, and seeing that, let me zoom in a little bit, right? You can't, if you find the area function from 2 points that are the same, it's 0 because there's no area. They're opposite if you integrate in the opposite direction. If we, again, it's about notation, us saying what's the area from here to here, going backwards, right? You can break up an integral. Two functions can be, and they'll have equivalent, right? It's the sum of them. The difference works also. A product, when you have a constant, you can just take the constant out and then calculate the integral value itself and then multiply the constant. That's what this says. So if it makes it easier, factor out the constant, and then, which we do quite often in the remaining part of this module. This is an important property, along with being able to break up a definite integral here into two pieces. So just keep those properties in mind as we solve. You see in here, we have these three you can see it's one function or three separate functions. And that would always, that's a way to think about it in our work. I think I want to end on, again, the idea of the average function value of a function. So it's an interesting thing. We've calculated averages before, like averages of a set of numbers, but how about the set of values of a function, right? We know a function produces an infinite amount of values over some interval, but what would the average value be for that? Well, we have a way to calculate that, right? There's a formula to calculate that right here. And so the average, but just, I want you to think about what would that mean? We talk about the average rate of change, but now we're thinking about what's the average value of a function? Very powerful idea, think of all the values a function has. What is the average value over some interval? Here's your formula for that. So it's not really complicated to solve. It's just really the concept of what do we mean by average value of a function? So again, it's worth going through the example, understand, see the function has a whole bunch of values. What's the average if we add up all those infinite values? Guess what? The area underneath the curve could do that for us, divided by the range of your x values. That's your b minus a. So it's an interesting application of the average value. Again, here we're still doing it by hand. It's a trapezoid, so you can use a trapezoid formula here to do that. So hopefully that's helpful, a little explanation of where we're headed. We'll move forward with using formulas and rules to calculate areas underneath the curve.